Yeah, thank you so much. Thank you for your invitation and for your nice introduction. The title of my presentation is actually on the recent advances in optimum stable pulse fiber lasers. This presentation is divided into two sections. One is semiconductor mode lock lasers and another on fiber lasers. So because to develop ultra fast and ultra short optimum stable fiber lasers, the most stable semiconductor mode lock lasers are required because they are used as a pump medium. Semiconductor mode lock lasers are compact, efficient, and robust pulse sources. They operate of the order of few gigahertz repetition rates and produce optical pulses from sub-pico to few femtosecond pulse duration. These lasers have huge applications in telecommunications and on laser pointers, and even on read and write data on a compact disk. So in this presentation, the device which we will investigate is actually quantum dash semiconductor mode lock laser. The cavity length of this device is around 20-30 micrometer, and the absorber length is 240 micrometer. This device operates at 21 gigahertz repetition rate, and during whole study, the temperature of this device was fixed at 19 degree. So this is the gain section of the device as well as the absorber section. The length of the absorber section you can see is 20-30 micrometer, and the absorber section length is 240 micrometer. So before starting experiment, first of all, we measure the optical characteristics of this device. This is the gain medium of the device where emission takes place, and this is optical circulator. The optical circulator collects lights from port 2 of the device, and from 3 we amplify the optical signal. Then this optical light is divided into two parts. One is used for the analysis of optical spectrum analyzer, and the rest is used for studies electrical spectrum analyzer. This is a device to plot its experimental diagram to plot its IV characteristics. So here you can see the at maximum pump of 300 milliampere, the laser it yields around 5 milliwatt pump power, and the threshold of laser is around 120 to 130 milliampere. Similarly, this spectra shows that the device is operating at 21 gigahertz repetition rates. And this is of the optical spectrum, and this confirms that the emission of the device takes place at 1550 nanometer and its range varies from 1550 to 5080 nanometer. So the objective of the current study is that the ideal signal should be like this one, when the pulse is actually oscillating inside the laser cavity. However, in reality, the laser have some phase noise associated with it. This phase noise actually called timing jitter as well, it's actually pulse train produced by mode lock laser shows some deviation of the temporal pulse position from those in perfectly periodic pulse chain and referred to as timing jitter. So the objective of this study is to minimize its phase noise, minimize its timing jitter, so that our laser could operate in ultra stable regime. So a few years back, a Japanese scientist they introduced the concept of optical feedback and optical injection technique. And the external optical feedback technique, in this technique, we reflect few part of light reflect back into the laser cavity. From here, you can see that few light here. This is one is a mirror, and the few light is reflect back into laser cavity. Due to this process, the dynamics of semiconductor lasers they changed a lot. They could be beneficial, and even they could damage the laser as well. It depends on how much feedback is actually reflecting back inside the laser cavity. So similar to optical feedback, there is another technique which is called optical injection technique, in which we use an additional laser. An additional laser source The light from this laser source is injected into this diode laser, and then the light isolated into this diode laser interact with this gain medium. Consequently, the dynamics of the laser changes. To start the measurements, first of all, we actually optimize our laser that at which feedback reflection our laser is operating at best regime in terms of stability. So here in this measurements, we can see that when the feedback strength, which is in the units of dB, when the feedback strength is increasing, the line width as well as integrated timing jitter is decreasing. So at the minimum maximum power minus 22 dB, the RF line width as well as integrated timing jitter, both are proportional to each. It's a minimum. So this shows that at this feedback strength, our laser is operating at optimum position. Its stability is best. So we fixed this feedback strength into this laser cavity, and then we started our experiment. Here you can see this is the schematic diagram of laser of the cavity which we introduced to enhance the stability of laser. So this is quantum dash mode clock laser. From port 2, the optical coupler, it collects light, and from port 3, the light was fed into the semiconductor optical amplifier. After semiconductor amplifier, the light was further divided into two parts, 50% into this cavity, which was further divided into two parts. One is called single loop feedback, when just one loop is connected, and additional loop, if you use, we call it dual loop feedback. So we investigate the stability of our laser when all these optical components which are introduced inside these loops were finely tuned. Like this one is optical attenuator, which controls the light inside the laser cavity. This is optical delay line, which change the length of cavity. This is polarization
Prof.
control.
Haroon, sorry to
Yes,
interrupt.
yes, yes.
I noticed that you are still on the first slide. The slide is not moving. Yes, correct. Okay, now I can see. I'm seeing experimental setup.
Yes, yes.
Okay.
Okay, okay. So should I move on?
No, sir, please continue.
Yes, yes. So here, this is the schematic diagram of our cavity. Before I present it 2 to 3 slides, I will just have will have a quick look on them. Due to some technical issues, maybe these slides will not appear. So first of all, this was the just basic introduction of semiconductor lasers, and I mentioned that we use this device, which is quantum dash mode clock laser device, which was used in this study. This 2030 micrometer is the cavity length, and 240 micron is its absorber length. This is the experimental diagrams which we and schematic of our cavities which we use to optimize the performance of our laser, and we just checked that okay, our device is operating at 21 gigahertz. The emission wavelength it actually varies from 1550 to 1580 nanometer, and the maximum output which we obtained from this our device was around 5 milliwatt. So the objective of this study is that the ideal signal inside the laser cavity, which oscillate between the two mirrors, should be like this one. However, in reality, this signal always have some phase noise associated with it, which results from spontaneous emission, vibration of the cavity mirrors, or it might be due to the variation in temperature. So here, this is a concept how we can improve the stability of laser, which is called field barrier optical injection technique. So here we used actually the few part of feedback light inside the laser cavity, which enhanced the stability of our laser, and we optimized that at minus 22 dB. We achieved best results, and we fixed this feedback ratio inside the laser cavity, and we started our further experiment. So this is the main diagram of our experimental study. In this experimental arrangement, this is the diode this is semiconductor diode laser, this is optical circulator, and this is the 3 dB coupler. After that, this is the optical attenuator, optical delay line, polarization controller, single mode fiber. There are various optical components which we put inside the laser cavity. And by fine tuning of these components, we actually optimize the stability of our laser. Just like all these components play their own role. 3 dB, it divides the light into two parts. Optical attenuator, it controls the strength of optical feedback inside the laser cavity, and optical delay line, it change the length of cavity. And similarly, the polarization controller, it changed the polarization of light. Similarly, single mode fiber, we use it to observe some interference effects at the 3 dB coupler, and then it was fed back into optical oscillator, and from here it was injected into the gain section of laser. So by using this schematic diagram and by using these cavity configurations, we study single loop feedback results and dual loop feedback results. In single loop feedback, when just one feedback loop was used to observe the stability of laser, in that case, we can see that the minimum timing jitter was around 700 femtosecond, and the maximum was 2.19 picosecond. In this case, the optical delay line, which we used in our experiment, was fine-tuned. And in these results, we claim that, okay, 700 femtosecond, our laser is operating at optimum position. Similarly, in dual loop feedback results, at around 70 picosecond delay length, we achieved our timing jitter at around 295 femtosecond. And on the basis of these results, we claim that dual loop feedback is most efficient than single loop feedback, and it enhances the stability of lasers many times compared to the free running case. The next slide, which is a sideband suppression ratio. Actually, when we use some optical feedback lengths inside the laser cavity, then due to those single mode fibers, there appear some modes in RF spectrum of the laser. And these modes, sometimes they are not required in many applications like frequency count generation. These modes are not required. So to filter these modes, we need some idea how we can filter them out. So we introduced a concept that if we optimize the length of feedback loops, then these modes can be effectively suppressed. And from here, from last plot, we can see that red one is the length, is the RF spectrum when the length of feedback loop was fine-tuned. And here we can see no frequency components is appearing and flat spectra is produced. So on the basis of these results, we claim that the RF spectrum in case of flat can be achieved without any frequency fluctuations by finely tuning the length of the feedback loops. So this is another technique which is called external optical injection technique. So in this technique, we can see that an additional laser, which is called slave laser, and it's actually tunable laser, CW tunable laser, and it was used to enhance the stability of a laser, and it was injected into this saturated absorber section, and from gain section, the light was collected into semiconductor optical amplifier, and then it was divided into single loop feedback. And here we can see, yes, in this slide, we can see that in case of free running, just the RF line width was 100 kilohertz. However, when single loop feedback was employed, then the RF line width reduced back to 2 kilohertz. And then when feedback as well as optical injection techniques were introduced, in that case, the minimum RF line width was 1 kilohertz. So this introduced the efficiency of optical injection techniques. However, this system is quite complex as we need an additional laser to inject it into the gain section of our slave laser. So these results tells us that by using external optical feedback as well as external optical injection techniques, we can enhance the stability of our semiconductor lasers. So now the second section, it is based on erbium doped fiber lasers. Similar, this is just basic about fiber lasers. Uh, in fiber lasers, the three components like pump, mirror, and gain. But in semiconductor fiber lasers, we replace pump with diode lasers, and the mirrors which we use, they can gratings in case of linear cavity, or they can be ring cavity. And the optical resonance or gain medium in the fiber lasers is actually the doped fibers, which could be erbium doped or ytterbium doped, depending on the wavelength which is desired. So this is the basic design of a erbium doped fiber laser, in which this is the gain fiber. These are highly reflective fiber Bragg gratings, output coupler which act as mirrors, and this is pump which is diode lasers. And similar to these, this is schematic diagram of erbium doped fiber laser ring cavity. There are a few components like wavelength gain multiplexer, erbium doped fiber isolator, saturator absorber, and then it was divided into 90-10 parts. So here there are few applications in which the pulsed laser is required. So normally the fiber laser operates in a CW. However, when you use some saturator absorbers, then you can force it to operate in a pulsed regime. To operate it in a pulsed mode, saturator absorber materials could be used. Saturator absorbers materials are actually those materials which possess nonlinear optical properties, and they absorb light to some extent, and when that threshold or extent is reached, then they start transmission. So we use these following characteristics, and we propose this cavity to investigate the pulse mode of our erbium doped fiber laser. And this cavity was formed here by using a pump source, then WDM, and optical isolator, which stopped the feedback reflection, then coupler. Few part of its reflect was reflected back into cavity, and few for the analysis like power meter, spectrum analyzer, oscilloscope, and optical spectrum analyzer. In this section, first of all, these results were measured by using nanoparticles in the form of powder. The cadmium sulfide nanoparticles were used, and the performance of our laser was investigated. And these material act as a saturator absorber, and here you can see that emission wavelength with absorber takes place around 1550 nanometer. Its pulse duration and repetition rate characteristics with the function of pump. When we are increasing the pump, the repetition rates are increasing, and resulting pulse duration is decreasing. And the minimum pulse duration was around 1 to 2 microsecond. And similarly, the RF spectrum shows that the laser is operating at 90 kilohertz, and the signal to noise ratio is quite good, 47 dB, which indicates the stability of our laser. Similarly, here in next plot, we indicate that how with the passage of time the laser behaves. So here we observe that laser is behaving stable as no shift in central wavelength takes place. So we claim that these observers are stable observers. So here we used thin film saturator absorber, and we investigated that by using this thin film on the core section of optical fiber, and then implement into the laser cavity. The performance of the laser can be enhanced. And here Q switch results were produced. However, the material was changed. In this one, a novel technique was used, which is called pulse laser deposition technique. This was the first time we used to fabricate saturator absorbers. In this one, actually the thin film was directly deposited on the fiber furrow, and then that fiber was implemented inside the laser cavity. And here we compare the results of this saturator absorber with those which were prepared with conventional techniques like nanoparticles based and thin film based. And here we claim that pulse laser deposition technique is an efficient and produces ultra stable saturator absorbers which have high threshold and could operate at high power as well. So these results indicated stability with passage of time. Here, you can see in red dots the stability of the lasers, in which the thin film, conventional thin films were used, is degrading with passage of time. However, the saturated observer, which was prepared using PLD, these results were stable. So on basis of these results, we claim the stability of our lasers. So this was the whole presentation. This is our group here at National Center for Physics, Qaid Azam University, Islamabad. So thank you so much.